Dr. Donna Shillington is a professor at NAU in the School of Earth and Sustainability. Her work includes marine geophysics, and she has been on 19 research voyages. Please give a big hand for Dr. Donna Shillington.
Hi, everyone. Good evening, and thanks for being here. As Brandon said, a big focus of my research is the geology underneath the seafloors. And one particular focus for myself and a lot of my colleagues are the geological settings that make the largest earthquakes on the planet. And one of our challenges in understanding these earthquakes is that the structures that generate them are underwater. In fact, a lot of our planet is underwater. We really live on a water planet. 70% of Earth's surface is covered in oceans. And although humans are landlubbers and we content ourselves to stay on the 30% that's dry, these oceans are really important to a lot of things in our lives. The oceans themselves regulate our climate by absorbing heat and carbon and redistributing it through circulation. The oceans host a lot of the life on our planet. And finally, the geology underneath those oceans is also impactful for us, including that some of these very hazardous structures that generate earthquakes are kind of hidden underneath the oceans. And now I'm showing you another map of our planet, but this time, instead of coloring all of the oceans blue, this map shows the depth to the seafloor. And the cooler areas are showing us deeper water, and the warmer colored areas are showing us shallow water. And if you look at a map like this, you think, all right, even though we live on a planet covered by water, we have a lot of this figured out, right? We know our planet pretty well. And wrong. That's actually not the case. There's only 8% of our seafloors that we've mapped in detail from a ship, collecting, high-resolution mapping of the seafloor. And that's shown in the kind of illuminated light colors of the map now. The other areas, which are the darker gray areas, are places for which we only have a fuzzy picture from satellite data. And the problem gets even worse if you want to consider how much we know about what's underneath the seafloor. And so we really have a lot to learn about our planet, especially the part of our planet under our oceans. From this map, maybe you can imagine that we know our own planet less well than we know the surfaces of some of our planetary neighbors. All right, so now I'm going to take you to the deepest parts of the oceans, ocean trenches. These are long troughs of very deep water that lie offshore of our continents. And the example that I'm going to show you is from offshore of Alaska. And so if we now zoom in on that area, in this map, there's the Alaska Trench is showing this very deep trough, this ocean trench that lies just offshore of Alaska and the Aleutian Islands. It's as deep as 6.5 kilometers. That's about 21,000 feet. You could almost put 2 Mount Humphreys down in that trench. Very, very deep. And this trench and other similar trenches that are like it are the surface expression of a geological environment that generates these really large earthquakes. So if we look under the surface, this is what we would see. These trenches lie at a tectonic boundary called a subduction zone, where 2 tectonic plates converge and an oceanic plate is thrust underneath the other plate. And at the boundary between these plates is where we generate these really large earthquakes. Over hundreds of years, stress builds up on that contact and then is released suddenly in an earthquake. And so when we look around the world at where earthquakes occur, many of them occur at the boundaries between tectonic plates, but the very biggest ones occur at subduction zones. And I bet many people in this room remember some of the most destructive subduction zone earthquakes we've had in the last 20 years. In 2011, a large magnitude 9.0 off of Japan caused shaking and a tsunami that resulted in a nuclear crisis at Fukushima. The 2004 event off of Sumatra caused a tsunami that was as tall as 51 meters locally. And that tsunami radiated out across the Indian Ocean and caused 200,000 deaths in 14 countries. These are huge and destructive events. And although scientists have known for a long time that this geological environment is capable of making these really big earthquakes, a lot of things about some of the recent ones we've had have kind of surprised scientists and shown us how much we have to learn. Some of these events were larger than we expected, or made a larger tsunami than we expected, and told us that we need to do a lot more work to really figure this out. And to kind of think about what those questions are, I'm going to again take you to Alaska, which had the second largest earthquake ever recorded in 1964, a magnitude 9.2. So if we now zoom in on Alaska, you can see in the upper right-hand corner the location of this 1964 earthquake I just described, but it's also had a number of other magnitude 8 or greater earthquakes over the last century. The most recent one was just last summer, a magnitude 8.2 earthquake that happened in July. This was the biggest earthquake that happened in the United States in almost 60 years. And so normally when you see maps of where earthquakes occurred, they look like this. They're plotted with a point, maybe surrounded by some concentric circles. But this doesn't really do justice to what actually happens when one of these really large earthquakes occurred. And so if we kind of come back to this cartoon again, this cross section through a subduction zone, and we can remember like how these earthquakes are formed. The contact between these two plates, which are moving towards one another, gets stuck, builds up stress over a really long time, and then is released in an earthquake. And one of the things that controls how large of an earthquake you have is the size of that area that gets stuck and then suddenly releases its energy in an earthquake. Bigger the area, bigger the earthquake. And another important factor for tsunamis is how close that fault slip happens to the seafloor. You can imagine if you were building up stress really close to the seafloor and releasing it, you would cause more motion at the seafloor itself, which pushes the water and creates the tsunami. And so now if we go back to Alaska with this in our mind, that the larger an area that kind of moves in an earthquake, the bigger the earthquake is, now we can look at these events again. And the dots are still there and where the earthquakes began, but now those large pink blobs are showing us the size of the area that actually moved during that earthquake that we've estimated if you like look underneath the Earth's surface down onto that subduction zone fault. And these are huge areas. For that 1964 earthquake, the area that moved was 800 kilometers long, 200 kilometers wide. It moved 20 meters over 4.5 minutes. So a dot doesn't really do that justice. And to kind of give you a frame of reference, that's like if we had half of this, an area half the size of Arizona moved the length of this room over a few minutes. It's just staggering the scale of what happens in these really large earthquakes. And so if as scientists, we could know how big of an area was bound up and then moving in an earthquake in advance, we could anticipate how large of an earthquake or maybe how tsunamigenic of an earthquake could happen in a given place. And so maybe you're asking yourself, well, this seems like an important problem. These are very destructive events. Why haven't you figured this out yet? And it's because it's really hard. These really large earthquakes, they only happen every hundreds to thousands of years. And so we can't just look back in history and say, oh, this is a place that has made a magnitude 9 before, maybe it'll make a magnitude 9 event again in the future. And as I mentioned before, the other challenge is that the geological structures that make these earthquakes are not only miles and miles underground, they're also often covered in water. And so they're really inaccessible to us and challenging to study. But there's many scientists around the world, including myself and my collaborators, who are really focused on this problem and trying to learn more. And a lot of the work that we're doing to study these places requires us to go out into the oceans and make observations on research cruises. Now, when I say the word cruise, you, like I suspect some members of my family and my friends, may think of something like this. Maybe there's a pool and some shuffleboard, some lounge chairs, fruity cocktails. No, there's no shuffleboard, there's no pools, there's definitely no fruity cocktails or any cocktails. But what research vessels lack in these luxuries, they make up for in their extraordinary technological capabilities. And so here I'm showing you an image of the Marcus G. Langseth. It's a part of the US's marine science fleet of ships. The ship is about 250 feet long. It can take about 50 people, including the crew and scientists, to sea for 6, 8 weeks. And it's chock full of all of this instrumentation that allows us to make observations in our oceans. And the first time I saw one of these research vessels, I was a 22-year-old first-year graduate student, and I was totally blown away at the size and the sophistication of these ships that were totally dedicated to science. I mean, that was amazing. And that a scientist could direct where the ship went and what it did. It really blew my mind, and the hook was in. And after that, I've been in this field for a really long time, and I've spent about 22 months of my life at sea altogether on 19 cruises, and it's been a real passion of my career. And I'm not one of these people that grew up knowing that they wanted to be a scientist. I never had a geology class in high school. When I embarked on my college career, I thought more of literature or art, and finally had settled on journalism until I took a freshman geology class to satisfy my science requirements for my degree and kind of discover this field that I'm in today. So, and the rest was history. But anyway, I digress. Back to these research vessels and how can we collect data from them that are going to tell us about this important problem of these geological settings that make these really large earthquakes. First of all, many of these ships have the capability for mapping the seafloor. And this is done from a sonar system that's mounted to the base of the ship. And it sends out a fan of sound waves that bounce off of the seafloor and come back, and enables us to make beautiful and detailed pictures of all the features that are on our seafloor and fill in some of those gray holes in the map I showed you earlier. And so here's just an example again from Alaska. The darkest colored areas are the Alaska Trench, this area of very deep water. But hopefully you can see some other smaller scale features as well. Channels where sediments are transported along the seafloor. There are seamounts, which are old underwater volcanoes. Some of the lineaments you can see are other smaller faults within the two tectonic plates that are converging here. Gives us a ton of information. But of course, to look at this big fault zone that makes these really large earthquakes, we need to also look underneath the seafloor at the structures there. And so to do that, we can actually use a similar method of using sound waves to map features that are removed from us. And so in this case, we send out our sound waves, and they not only bounce off the seafloor, but they bounce off of structures below the seafloor, including this big plate tectonic boundary where these earthquakes occur. And we can record those sound waves on a couple of different kinds of equipment. One is a long seismic streamer. It's a cable filled with pressure sensors. They can be up to 10 miles long, so it's a lot of equipment to drag behind a ship. But we also are able to put out autonomous ocean bottom seismometers. These are instruments that sit on the seafloor and also are very sensitive and can record returning sound waves. And we can use this combination of observations, of recordings of these sound waves to make pictures of the Earth. And before I show you an example of that, I just want to show you a few pictures of the equipment because, it's cool. So here's an example of one of these ocean bottom seismometers. It's about to be lifted over the side and lowered into the ocean and sink to the seafloor, where it can sit for days, weeks. Some of them can stay for over a year. And that instrument has both a sensor that records the ground vibrations, a computer to record them, a battery pack to power the instrument, and other instrumentation that allows us to communicate with that instrument while it's on the seafloor. They're super impressive. And to me, it remains amazing. You can take this ball of electronics, chuck it into the ocean, and it does something valuable and then comes back to you. I mean, it's magic to me. And the other type of equipment that I mentioned to you are these long seismic streamers, 10 miles long. That's a lot of cable. And so we store it on the back of the vessel on these gigantic spools that we unroll into the ocean to deploy it. And that takes almost a day to put the entire 10-mile long cable out behind the vessel. We monitor all of the data that are acquired on this in a science lab. And so here's a picture of that. There's 47 monitors that we'll show you images and updates on everything about the operation of the ship. The students sometimes call it the Bat Cave. It feels very much that way. And we're able to, monitor our full operation from there. Okay, so I've told you about all of this equipment we have on the ship, how amazing it is. So what kind of things can we learn? And so I'm going to show you an example of an image from offshore Alaska to give you a flavor for what these kind of data show. And this is basically like an X-ray underneath the seafloor, and we're looking at a cross-section through the Earth. So all the light blue colors are the ocean, and then below that I've kind of colored in some of the main geological units that we see. And so if we start on the right side of that image, we're seeing the oceanic plate before it enters into this subduction zone. And the yellow colors are the sediments, and hopefully you can see some flat-lying layers in there. These are sediments deposited on the oceanic plate over its lifetime. Below that in green is the oceanic plate itself. And that plate is moving down and being thrust underneath the continental plate, which is in orange. And as it goes down, you can see that some of those sediments that are just riding along on top of that plate get scraped off, faulted and folded. Those are kind of the dipping layers in the middle of this image. But the other big thing we can see is we can image the fault zone itself. And we can learn something about its properties. How thick is it? What kind of material might be in there? What are some of its basic characteristics? And if we collect these kind of data over multiple lines across the subduction zone, we can start to make a map of what those fault zone properties look like. And the idea is that by comparing those properties with where these earthquakes occurred, in particular, what are the properties inside of those big places that built up stress and moved in an earthquake? And what are the properties inside and outside of those zones? And if we could make a relationship between properties of the fault zone and whether or not it moves in an earthquake, we could have a chance to make a map of how big of an area was likely to move in an earthquake in a given place. So this is still very much a work in progress. We've made excellent progress so far, but have a lot more to learn. And I've described to you one of the methods that we're using to study these really large earthquakes, seismic imaging. But it's most powerful when it's combined with a lot of other kinds of data. There are scientists who are drilling the shallow part of this fault zone to actually get back rocks that are from the zone that's moving in these earthquakes. We can put out instruments for a long time on the seafloor to listen for small earthquakes or to monitor seafloor motions. And combined, we're starting to make progress on this really important problem. But doing so has involved not just the kind of data I've described, but many others, and a lot of them are out in the oceans. And in general, our oceans are home to many important scientific topics that require us to go and explore in our oceans. So thank you very much.
That was great. Thank you.
Thanks.
All right. I promise I had a question. What causes the tectonic plates to move?
Thank you. So something to remember is the tectonic plates are moving so slowly. The common thing geologists will tell you is it's at the rate your fingernails grow. And their motions are actually driven by the sinking plate in subduction zones. That plate it's dense and cold, and it wants to sink, and it sort of pulls along the rest of the plate with it. And it gets an extra push from another kind of plate boundary in the middle of the oceans, a mid-ocean ridge, which kind of pushes them apart. So, thank you.
Terrific, thank you. All right, one more hand for Dr. Shillington. Our next speaker is David Van Ness. David is the founder and co-coordinator of the new media art emphasis within the School of Art at NAU. David was born in Texas and came to Flagstaff in 2011 to run the first-year program at the art school. He lives just outside of Flagstaff with his wife and 2 cats. Thank you, David.
Thank you. All right. First, one word of warning. I will be mentioning suicide ideation. So those of you, particularly those of you online, if that is an issue, please consider this a little heads up or warning. And I also, if I end up crying, it's no big deal. It is what it is. As Brandon said, I am David Van Ness. I am the founder and the co-coordinator of the New Media Art Program. So what does that mean? It means that I am the guy who is the mad scientist, something I happily embrace. Because my field is really an intersection of the arts, the sciences, and anything really that is experimental and so forth. So tonight I wanted to talk about my mental issues that I had in 2020 and how through that I sort of found a new body of work and how I came through it with my work itself. And so I have been an artist all my life. Unlike Donna, I actually knew what I wanted to do when I was a little kid. I drew all the time. And I always was the kid who was always making art and always playing with anything that they could get their hands on. So the interesting thing is I probably was also dealing with mental health my entire life. I did not know this until my late 20s and my 30s. And it was actually, for some kind of ironic, in that in my 30s, I moved here to Flagstaff to be the coordinator of the Foundations program, the first year program at NAU. And that is a dream job. I mean, I was 1% of the population. I was teaching art. That is what I wanted to do. But mental health doesn't care. And it came anyways. And I would be facing that. And I often would find myself depressed and anxious and so forth. And when I moved here, I was finally able to see a therapist. I got a diagnosis of anxiety. I got a diagnosis of depression and handled them, at least I thought. Then 2020 came. And I don't know if you all remember, but there was a pandemic. And we all had to deal with it in our own ways. There was isolation. There was issues of course, being ill and potentially losing friends and family. And there was just an overall layer of anxiety I felt. I think we all felt it probably. I had a little bit of a problem. I tended in my moments of isolation to doom scroll, like many people. And in one of my doom scrolling phases, I happened to come across a video by Legal Eagle covering an issue from MXR, another YouTuber, who was doing a response video. MXR had used a video piece from Junkin Media. Junkin Media is a corporation that produces short video for makers and YouTubers, and they then ask for royalties and so forth. Well, MXR didn't do that, and it became a huge issue. Something triggered in me. I'd recently done a series of work in which I had actually utilized Confederate monuments, as you see one here on the right, on your right. What I had been doing was I was taking Confederate monuments, combining it with 10 years of hate crime data to really express the true legacy and the true history of these things, because a lot of these statues were ordered out of catalogs during the Reconstruction era to reinforce very repressive ideals. And it's something that I really was passionate about. I grew up in Texas, and so Confederate monuments was around. History of the Confederacy was totally different, maybe, than what it really was. And so I had a sort of a skewed view, and I kind of wanted to sort of realize what that was and sort of work through it myself. The thing is once you sort of think about, oh my gosh, maybe I utilized digital imagery in my work. I utilized digital 3D scans often, and I would get them from open source libraries, or I would get them from royalty-free licenses online. I would purchase them. Well, I used one. I used one for that particular Robert E. Lee statue. It was a 3D scan from New Orleans of the Robert E. Lee from Lee Circle. And I had used it because it was a Creative Commons license. I was shared. I didn't realize that Creative Commons, which is the sort of the copy left, which is the counterpart to the copyright idea, had other aspects to it. And one of those aspects is non-commercial. Well, I had used it, I had created some work, and I literally had a piece in hand. And at that point, I discovered that this piece had non-commercial and so forth. But what was I to do? I had already started the piece. I had made this new work, and I had started building. And so I immediately began to sink into massive depression. I would call friends and family. Poor friends and family got to hear every little aspect of any potential harm that could come to me. I was thinking that people would come find me and ruin me. I finally proved that I was a fraud. As many academics can tell you, we probably all have a little bit of imposter syndrome in our lives. But so I knew it. I mean, I looked for this long enough and I found it because, you know, as I said, you look for something long enough, you will find it. And so I really got bad. I mean, I sunk to the bottom. And sometimes, as I've talked with my therapist, we've said that sometimes you do have to hit the bottom before you can really kind of come out of it. I thought I hit the bottom previously, not like this. And something different had happened. And I didn't know what to do. But something was still moving. My work was still being done, and I was still doing some things around. And through this, I ended up getting permission to utilize the file. But it had destroyed me. It had ruined me. I was no longer interested in this body of work. I thought, what am I doing? I may not be the right voice to even speak about this. And so my work utilizes a technique known as 3D glitch. And 3D glitching typically is a way of manipulating a digital file mathematically, sometimes in Microsoft Excel, the most exciting art tool ever. Or sometimes, like on the Buffalo there, I had actually manipulated the program to edit the file in a different way. And so what is going on is I am essentially moving vertices. So 3D models are made up of vertices and face definitions. And my early work really focused on those vertices. Those vertices are the intersections of all the little triangles that make up your form. And so I would push these forms by adding new data, maybe manipulating things, maybe even removing stuff, and then letting the machine kind of rationalize what I had just done. I saw this as a collaboration between myself and the computer. And for years, this is what I did. I had a mastery of a trick, I felt. I felt that I was able to sort of make these little shiny objects that just were very interesting. And as an artist and as an academic, I needed to define myself. And I really was one of the first artists to really work in 3D printing. I was part of the 3D print show in London. I was part of many exhibitions around the world and throughout the country about 3D printing. In that, I was always interested in about the media, and sort of glitching was my way of sort of rationalize my understanding of is my media the digital file? Is it the 3D print, or is it something else? And so as I sort of worked on these forms, I became interested in the idea of data, because I was just pushing and pulling and moving things around randomly. I wanted to find a way that I could utilize the data, the pieces that move my models around, that edit my and create the glitching, and connect that directly to the meaning or the form or the look of the piece. What you see before you is on the far left is a protein made from Beethoven's Ninth Symphony. Because I could understand that I could translate data to data, it was just numbers. I was able to start going in different fields. I was in biology, I was doing music. I'm not a musician. Heck, I even thought music was a two-dimensional ray. It's not. I learned that one pretty quickly. On the other two pieces, those are actually self-portraits. I wanted to find a new way to sort of create a portrait. Those portraits are actually my Fitbit data, my social media data, and my DNA. Printed at the microscopic level, and then coated with stem cells, and then tagged, originally going to be tagged with my own DNA. Time and whatnot sort of prevented that. And so this is where I was. This is what I was making when I started to shift over to the Robert E. Lee pieces, because I felt like I had something to say. But now, I didn't know what I was going to do, and I was kind of lost. And what was interesting is in this period, I began to sort of think about myself. I mean, obviously I was turning inwards a lot. There was a lot of mental health. I was really turning inwards. I was reading a ton of stuff, and I was really exploring what this really was, what I was dealing with. And I have these skills. I have these skills of manipulating data, taking things, and what you're looking at now are 3D scans in my own head, combined with CDC data on mental health. And these are all different self-portraits. One is depression, one's anxiety, and one is OCD, the one that's changing color. That paint has actually changed because of the heat of the thing in front of it. But this is where I started sort of mining things, and I found that, you know, really, if I look back at my work, and I know a lot of artists do this, but I began to understand that everything I had done was a self-portrait in many ways. And I finally have acknowledged it and said, you know what, I don't need to do what's cool. I don't need to be that innovator. And I found something that I was really, truly passionate about. This is has consumed my work now. And I have a new exhibition coming up in 2023 that will deal primarily with mental health, but it's also going to introduce things that I haven't dealt with a long time. I'm known as the 3D print guy, and I'm fully aware of that. Heck, in Flagstaff, I'm known as the tortoise repairman because of some projects I've done. But with this discovery, I found that I'm able to talk about things in different media. I'm now looking at things of robotics, light-controlled pieces, all these medias that I'd sort of abandoned when I found 3D printing in 2008 or so, I forget exactly when. But I'm now returning to some older media. Heck, I'm even making a giant teddy bear for my project. So I'm really exploring different areas, and I've really sort of found that this has become my niche. And it's not the technical that I thought I would be defined by, but it's the conceptual and the ideas and the idea of mental health. And so this is where I am now. I'm in process. These are the 3 newest pieces out of the studio. I have several works that deal with, like I said, with robotics and lights. But I see myself now as one of the big proponents of mental health. And it's something I deeply care about, and it's something that I want to express. I want to make a safe space in my work, in my exhibitions, for people to feel safe to talk about it, because we don't enough, and it should be talked. And you should talk to your friends and family, and if they don't respond, maybe it's time to get new friends and family. But it's important, you know, and as an educator, one of the things that I definitely do see is that my students, my younger generations, are much more open about it, and it's time maybe for some of us old people to actually listen to them, because they're much more open and much more honest, and it impresses me every day. So if you have any problems, please reach out. Somebody cares. Somebody cares. And that's all I can say is please take care of yourselves. Thanks.
All right. That was a great talk, David.
Thanks.
I really appreciate it. It takes a lot of courage to come up and share so much. And you obviously share yourself and all your work. So you had some experience.
Yeah,
but
a little bit.
It was great. In some of our previous conversations, you talked about how you were making the shiny objects. You were chasing the 3D glitching. You looked at it like, this is really cool. But then there's some introspection that kind of helped you say, well, I really want to make something that's meaningful to me, and I want to share something that has a deeper meaning. So this has been a process, obviously.
Yeah.
For the artists who are in the audience, for home watching or watch the video in the future, is there something you can share about how to look for finding meaning in your art as opposed to the chasing the shiny, or even how to know the difference between the two? Like, if it's probably not obvious when you're in the midst of it.
Yeah, and that is a really interesting question, because my answer would be to do the work and to do more work and constantly just kind of do the things that are at the front of your, that you can think of right in that moment, and build those things, and then sort of sit back and reflect. Because it's really sometimes, as a builder, as an object builder, I've always been an object builder, I tend to build and just kind of go ahead. And then as things move, meaning sort of gets pushed into the things. And I began to see the meaning sort of arise out of just the sheer labor. Sometimes it is very evident, and sometimes I do have a sort of a goal and plan, but other times literally it just arises as I work, because I've now, being on the other side of this kind of thing, I have a passion and I have a goal, and things are built from that. And so I'm pulling it from there, and I'm not necessarily looking at my individual works. And so for me, it really was trying to find that thing that I cared that much about, and really sort of, and in my situation, it's part of me. You know, and so it's really part of who I am.
Thank you.
Yep.
It was excellent.
Thanks.
All right, big hand, David. All right. Our next speaker is Dr. Jennifer Wade. Dr. Jennifer Wade is an assistant professor in the mechanical engineering department at NAU. She works in the area of engineered climate solutions, working with new materials and the processes that they enable. This big round of applause for Jennifer. Have fun.
Thank you. So thanks for being here tonight, and thank you for having me as part of the panel. So for decades, we've all been hearing about how our human-caused emissions are causing global warming. And with each new season, we're learning, sometimes painfully, what the consequences of that warming are. So for the next 15 minutes, I don't want to belabor the problem. We know the problem. I want to instead focus on the solutions. And very specifically, I want to focus on a solution that addresses the technical cause of climate change, the greenhouse gas emission. Okay, so for the next few moments, if you'll bear with me as I use a bathtub as an analogy for our atmosphere, as we discuss what we call our greenhouse gas budget. Now, briefly, a greenhouse gas is the molecule that gets released when we burn fossil fuels or when we change our patterns of land use. And when these molecules get in the air, they're really good at absorbing the heat that comes from the Earth's surface, and they like to radiate it in all directions, and one of those directions is back down. So essentially, they're acting as a blanket. So thousands of scientists have come together to decide how much of this greenhouse gas we can let flow into our bathtub before we start to overflow. And what I mean by overflow is uncontrolled warming. So in order to understand how to manage this budget, we have to understand what is causing. Where are all these greenhouse gases coming from? What are all those faucets draining or pouring into our bathtub? So the solution of how we manage this budget feels pretty obvious. We just got to turn off those faucets, right? We just have to turn them off. Well, before we do that, we have to appreciate, frankly, the diversity and the complexity of what all those sources of greenhouse gases are and where they're coming from around the world. Now, this slide is a very complex, cool plot. It's called a Sankey Chart. This one was provided by the World Resource Institute. And the reason why I'm showing it here is not to lose you because you're trying to figure out what's going on. It's because I want you to appreciate the diversity and all the different kinds of emitters or faucets that we have that are leading to these greenhouse gas emissions. Some of these emitters we're all very aware of. That first picture is taken from Page. That's the old Navajo generating station that no longer is in the landscape, but our power sector is a major contributor. All of the things that are surrounding us, that we're sitting on, that we're wearing, that are operating, those are materials that require heavy manufacturing. That is a major faucet that's filling up our bathtub. Our transportation sector, our agricultural practices, and even our waste that get into the landfill. These are all those faucets. Now, if we turn these off right now completely, it's going to require massive social, economic, and technology transformations. And many times we know what we need to do, and those are economic solutions. We will go after them. But if we do all of it all at once, we may cause unjust harm, especially to populations that have hardly contributed to the problem in the first place. And now is just a really good time to remember that to date, the United States, the wealthiest nation in our world, has contributed the greatest cumulative amount of greenhouse gas emissions. And it's with that burden that we look forward to the solutions. So it turns out, in addition to all of these faucets that's been filling our bathtub up with greenhouse gases, there's also quite a few drains that are available to us. One major drain, or sink, as the scientists call them, is our ocean. It has very slight alkalinity, and for years it's been slowly absorbing carbon dioxide, our most abundant greenhouse gas, because it's slightly acidic. Now, that is not a sink I am hoping to accelerate, but there's some others. The other obvious ones are our biosphere, so our forests and our wetlands. These are using natural photosynthetic processes that pull the carbon dioxide out of the air, trapping it as that biological hydrocarbon. There's also our geochemical cycles that I'll talk to in just a moment. So if we can't get those faucets off quickly and we can't turn them off completely, well, then we better start looking at what we can do to accelerate the sinks. And that is where I spend a lot of my energy. Now, thousands of scientists have come together to say, look, we have to start turning those faucets off now, and we have to start turning them down pretty fast, as evidenced by that red elbow in the curve there. That's what we need to do right now in order to limit the warming to only 2 degrees Celsius. Now that 2 degrees Celsius, or more aspirationally 1.5 degrees Celsius, this was the amount of warming that was decided upon in that Paris Accord Agreement back in 2015, that legally binding international treaty that's going to hopefully hold us accountable to how much greenhouse gas we put into our bathtub, the atmosphere. But nearly all scenarios know that just turning down those faucets is not going to be enough. We also have to get the greenhouse gas out of the atmosphere, and we have to start doing that by the end of the decade. And by the end of our century, we have to start doing that to the tune of 10 to 20 billion tons a year. Now, exactly where we land and how much we have to remove depends on how fast we can turn off those faucets, how fast we can come off our fossil fuels and our land use practices. Now, if we have to get that negative emission, if we have to accelerate the sinks, let's pay attention to what those sinks can be. So I already mentioned the natural biosphere. And as plants start to accumulate CO2 and building them into hydrocarbons, the living matter itself is a storage reservoir that will last for decades to hundreds of years if we can sustain that. As that material breaks down, it can be incorporated into our soils. Our soils can be a massive reservoir for all of that carbon. Our wetlands and coastal habitats are also really excellent reservoirs for that carbon dioxide, which is our most abundant greenhouse gas. The key there is we have to make sure that it's storing more than what it's already doing, and we're not reversing those changes, which means a lot of enforced land management policies for generations to ensure we have permanent storage. One other thing I just want to say about that sink is it'll do a lot for us, but it can only do so much because that land that stores that carbon is also providing another important activity, and that is providing us food and fiber. So we have to do more than just relying on those natural sinks. Another natural place for this carbon, and now I'm speaking very specifically about the most abundant greenhouse gas. So another obvious place for that carbon to go, carbon dioxide, is put it right back into the ground from which it came. And the reason why that's a good idea is because we know for millions of years, those porous volumes in rocks were trapping hydrocarbons, which was the original source of the carbon before we combusted it for our energy systems. Now we need to make sure that it gets down there far enough under several layers of dense rock. We want there to be tiny pores to trap it using a phenomena called capillary forces. And it's also really great if there's saline aquifers down there, saline water, something that's not our drinking water, because that also will ensure it stays down there and stays there safely. But we certainly have to monitor it to make sure it's not interfering with anything else and it doesn't come up catastrophically. Now, the holy grail of storage is storing it as a solid. So allowing that slightly acidic greenhouse gas CO2 to react with our slightly alkaline minerals that are all over Earth's surface to form a carbonate rock. So I have a couple of props here today. This right here is trapped CO2 in the form of a mineral. I took this right off the NAU campus. This is our Kaibab limestone formation. You can also see this in the Grand Canyon. So this is a calcium magnesium carbonate rock that at one point in time reacted with CO2 and silicates. Also in Arizona, we have a whole bunch of these silicate minerals. So silicates tend to come from our volcanic geologic formations. This is taken from one of our young cinder cones in the region. And it happens, this particular sample that I'm showing you is in my lab because it has a lot of natural alkalinity in there. And so when I mean alkalinity, I'm really talking about magnesium and calcium in these materials. And the job of the engineer is to figure out how not to do this over millions of years, because that's not the rate that we're emitting. But we have to be able to accelerate this so we're hitting 10 to 20 billion tons a year. And so that's where I help think about the problem. What do we need to do to accelerate this process and get it into this state, which I haven't said already, is the thermodynamically most stable state for that carbon to exist in on the surface of our planet or near the surface of our planet. So what do we do to try to accelerate that sink? The first thing that's really helpful is if we can take that greenhouse gas, which is still very dilute in the atmosphere, roughly every 4 out of 10,000 molecules is a carbon dioxide molecule. And we want to be able to trap it. And the way we trap it is we put a material into the air. And the materials I work with look no different than an index card. So I brought an index card tonight because we're treating them in the lab. I didn't want to bring them here. Looks no different than this, but it has a high affinity for the carbon dioxide. Why? Because it's alkaline. We're taking advantage of that high school chemistry acid-base process. So one of the tricks is, how do we do a good job of making sure we can pass all this air, pass these materials so it can trap sufficient amounts of carbon dioxide, and hopefully after it passes by, it's now less, it's even more dilute, which is our goal. We want less of it in the atmosphere. Now, the next step is, well, if I then took this material with all the carbon dioxide on it and I put that underground, that would be a problem because these are material inputs. And they cost something. And we want to make sure this is going to last for as long as possible. So we're going to want to cycle it. And to cycle it, there is the energy input. So we took advantage of some thermodynamic chemistry to get that CO2 trapped. We have to overcome that again to pull the carbon dioxide back off. All first of kind demonstrations that are already doing this take advantage of heat to remove the CO2, the carbon dioxide, from this material. Some of the first demonstrations needed really high temperature heat. That, of course, required a fossil fuel combustion. We want to move away from the combustion of fossil fuels. More recent materials are taking advantage of lower temperatures. That's handy because then we get to use renewably powered heat pumps to generate that heat, or maybe we have a waste heat stream, or maybe there's a nice geothermal source underground to help us out. But what I actually work on are materials that don't necessarily need heat to release that CO2. Here's a cartoon from a project that I'm on. We're actually taking a look at using moisture as our energy input. So when we hit these materials with water, this water vapor, which by the way is in the gas phase that we don't see, right guys, from the earlier trivia question. So when we hit this with water vapor, the CO2 likes to release. So one of the projects, I'm involved in several projects with these kinds of materials, is looking at, well, now water's our input. So how do we become as efficient as we can with that water? How do we best exploit this response? And how can we cycle the water using natural evaporation processes? Other colleagues around the world are looking at just simply applying an electric field to these materials to get that carbon dioxide to go. I'm looking at a combination of all of the above to try to get that CO2 to release, because the goal is we want it to be nice and concentrated. Once it's concentrated, it'll more quickly react with that solid mineral to get ourselves into the most stable state, which is as a carbonate rock. So other things that we need in order to get this thing to go quickly that we look towards is water. It's really good at trapping the high pressure CO2. It's also good at dissolving that rock. We also want surface area. So the figure on the slide is actually a core from a basalt deposit. So basalt is a form of silicate. This one's from Iceland. And those crystals that you're seeing there are the carbonate that's formed when it was injected underground. So they drilled that and pulled it back out of the ground to convince ourselves that in fact it did react to form the carbonate. But also what you'll see in that picture is there's a lot of pores in there. There's a lot of surface area, and that's indeed what we need to get the reaction. And so the silicate that I showed you just a minute ago, here taken from one of the Miller mine sites. So this is actually being quarried right now. We use this for the grit on our roads in the winter. When the roads get slippery, you can buy this at Landscape Connection. This material naturally comes to us pretty porous because of the way it was formed from those gaseous volcanic eruptions tens of thousands of years ago. So we look for surface area. You can get it by grinding and crushing. We're not really in the mood to do too much grinding and crushing because that is another energy input. Anything we do energetically hurts the negative emission. The other things I look at are catalysts. These are the ingredients that help accelerate the rates because after all, that is what we're trying to do. So the good news is about all of this, because I know this is a fairly new field, is that there are several first-of-kind demonstrations already established in separating that carbon dioxide directly from the air. We call this direct air capture. Injecting that carbon dioxide now as a high-pressure supercritical fluid is what we call it. And we have evidence that these things are reacting pretty rapidly over several years. What I'm doing as an engineer is trying to find new materials that are more energy efficient, that are more affordable, and are faster, so we can get more of those negative emissions with the fewest amount of inputs necessary. And then finally, in wrapping up, I want to remind you that no one actually wants this bathtub to overflow. No one wants uncontrolled warming. So what we need to do is we need to turn off those faucets using the technology that we know is available and that is economic to use. And we also must accelerate the sinks. Thanks.
It's great. Thank you.
Yeah.
You know, it's not easy to have a talk about climate change. A lot of times people are, skeptical or they've heard this before. But I love how you focused on, okay, yeah, climate change is here, but now we're focusing on what we can do to make things better. So my question is kind of similar. Mm-hmm. Now that my kids are a little bit older, and now they can at an age where they could understand global warming. How do we educate them on the problem without them becoming kind of apathetic? I want to be able to say, hey, it's a global problem. We all have to work together, but there's things that we can do that actually make things better ourselves.
Yeah. So I'm going to tell you there's days when I'm like, what did I actually accomplish today? Do we have that better material? Do I understand it a little bit more? And I can get really frustrated just in the act of science, right? We can get quite frustrated. So on those days, I remember that there's individual choices I have. And maybe that's my family deciding we're going to have a plant-based meal tonight. Or maybe that's deciding that I'm gonna make my kids ride their bikes to school instead of idling my car in the bike lane. She's laughing because she knows I did that. But also what I wanna say is I'm just an engineer talking about how I approach the problem. We need more students going into science and engineering to help us with this problem, not just to accelerate the sinks, but also to transition our energy sectors over to renewably powered sectors and to improve our land use and agricultural practices. We need that capacity. But more than that, I remind you that it's more than engineers and scientists working on this problem. We were part of the problem, we weren't the whole problem, we're gonna be part of the solution, we're not the whole solution. We need everyone to do all the things. And we need all the disciplines to find their way to help contribute to this problem, even if it's the policy, legal teams, if it's the financing to figure out how we're going to funnel human wealth to solve this issue because it's not happening for free. Or even if it's just the artists and the communicators helping the world understand why this is such a big problem. We need all hands on deck to help us in all the ways possible. The other thing I just want to say is we're going to try to do this with the least amount of impact as possible, trying our best not to make the big mistakes. We might make some mistakes, and people are going to keep watching us and holding us accountable to make sure we're learning and those mistakes stay small. But we should be supportive of all the kinds of solutions because we're going to need them all.
Excellent.
Yeah.
Thank you.
Thanks.
That's great.
Give this to the next.
Okay. Take some of these toys away. We have one final speaker tonight. Muan Hen holds a BS in Conservation Biology and Outdoor Recreation Tourism from the University of Idaho and a Master's in Science in Environmental Sciences and Policy from NAU. She is Executive Director at Willow Bend Environmental Education Center, leading hundreds of environmentally focused field trips, tours, community events, workshops, and in-class programs. She has 2 adventurous daughters. Together, they love exploring, hiking, and horse riding. Hi, Muan.
Good evening, everybody. My name is Muan Hen, and as Brandon mentioned, I have the privilege and the honor to run Willow Bend Environmental Education Center. For those of you who don't know, we are a full-time, year-round environmental education center here in Flagstaff, serving the entire county. Today, I'm going to tell you why I became an environmental educator and how each and every one of us can practice effective environmental education. I'm going to start with a story. This is my own personal story. This story happened about 13 years ago when my oldest daughter was about 3. And I really wanted her to experience nature. And I wanted her to see wildlife in their natural settings. And I knew she'll probably be going to preschool soon, and maybe she'll visit a zoo or something like that. And I wanted her first experience with wildlife to be outdoors. So I packed up a toddler and an infant and drove 16 hours to where is the best place to see wildlife in Northern America is Yellowstone. So we made it to Yellowstone, and of course we saw amazing views, and we saw elk and deer and bison and the occasional coyote. But I was really hoping to see a mega predator. There's just something about seeing these predators in the wild that really affects us as humans. Luckily, on the very last day, as we were actually driving out of Yellowstone, I spot a bear on a ridge, and not just a bear, but a grizzly bear. And I'm so excited, and I get this toddler out of the car, and we're basically running to see this bear. And I'm like, wow, look, a bear, oh my gosh, a bear. And I turn around, and I see that my toddler is not right next to me. So first of all, bear, where's the toddler? But also, I want to see what she's doing, and I turn around, she's on the ground, she's crouched on the ground, and I kind of run back, and I'm like, look, bear, bear. And she's focused on something completely different. And I look down and I sort of crouch next to her, and she says, Mom, look, in the quietest voice that a 3-year-old can utter. And I said, what are you looking at? She goes, a purple flower. And I had a moment there, because I'm like, bear, bear. But I took a second, and I will tell you what happened as we progress today. Because what I'm going to hopefully share with you today are the 3+1 main guiding principles for effective environmental education. And one can argue that really the minute we're outside with our kids or students, we are already, in effect, providing environmental education experiences. But I'm going to differentiate a little bit, just going outside and actually, again, providing effective environmental education programs. So the first thing, that's my +1, is just get out. So get your kids out, students, friends' kids, whether we're a formal educator, a teacher, non-formal education, a parent, a friend, a relative. It's really important, and there's endless research, and I won't go into all of that now, of why it is important to just get out. And it really doesn't matter. It doesn't have to be Yellowstone. It doesn't have to be a 16-hour trip. It can be outside in a schoolyard. It can be in our amazing trails. And it can actually even be in a parking lot. So first of all, we get out. But after that, there are 3 really important things that really important principles that we can do. And those are the principles that we really uphold at Willow Bend Environmental Education Center that really makes a difference between just getting out there, which again is important in itself, and really elevating a child's experience into effective environmental education experience. The first thing is to spark curiosity. We spark curiosity and we provide a positive experience with the natural world. So going back to my story, we got out, we got to Yellowstone, and really I was trying to spark the curiosity of a giant mega predator, the bear. But my daughter, her curiosity was sparked by something else. And it is my role as an educator, as a parent, to follow her lead. And again, provide these age-appropriate, time-appropriate opportunities for children to explore their own curiosity and engage with the natural world at their own level and their own interest. But my role was to spark that curiosity and follow her lead. The second important thing is develop skills. And there are endless skills out there that we can develop, but really it is skills or a knowledge base to explore and understand the environment around us. Going back to my example, it is asking questions. Wow, what do you think this flower's role is in the environment? Who might eat it? Why is it here? Why is it purple? So these are all questions that we can ask to change an experience from just enjoying something, which has its place and its time. But again, if we're practicing environmental education, this is the principle that we add, asking questions, and then later providing the tools. Again, age and time appropriate. These tools might be as simple as a hand lens. They can be water quality testing kits. They can be a microscope. They can be more advanced technological equipment, and they can be really basic. But it is our responsibility and our role to provide those tools and develop these skills. And again, this is child-led. So different children will naturally gravitate towards different skills. Formal education says we have to sort of educate everybody with the same skills, but we also have the opportunity to give children and kind of enforce and encourage their own interests and their own skills. And lastly, but definitely not least, is we have to foster a sense of responsibility. So we foster a sense of responsibility and love and care for the natural world through sort of personal experiences, right, and role modeling. Going back to my example, I could step on the purple flower and call attention to the bear, or I can really foster a love and care for what she's looking at, the purple flower and the world around us. We can do that by just naturally, again, walking through our environment with care and responsibility, or we can actively, we can take our children, our students to volunteer, trail cleanups, and even grander things than that. So it really starts with us, and it starts with role modeling and what we show them that we care about. In my job, I have the great honor of potentially taking your children, our students, on different field trips. Every place we go, we try to lead by those 3 principles. Again, sort of spark that curiosity, have it be student-led, develop skills depending on where we are and what the focus is, and then lead by example and share that sense of responsibility and care for our natural world. We explore, we ask questions, we provide tools, we look, we feel, we start young and enjoy, so we're always students at any point in our lives. That was not in my job description, but we also maintain a sense of humor. These are my daughters today. And going back to that story, people always ask me, what did you do? So yes, I stopped. I crouched down. We talked about the purple flower as I saw the bear disappearing into the horizon. But really, I think that that story and that lesson is what brought me here today and gave me the immense privilege and honor of doing what I do. Thank you.
Thank you. It's a great way to end SCI Talk. Of course, I got a question for you as well.
Perfect.
And we're going to keep this between the audience and the people online. So we know Flagstaff, great place to live. One of the big reasons, we can get out in nature really, really easily. So if we were looking for maybe like a super secret area that maybe you and your daughters really enjoy, that you just wanted to share with us as a great place to bring ourselves as lifelong learners, our kids too, to enjoy, be curious, and most importantly, get out, right? Any recommendations?
Yeah, so I'm actually gonna diverge a little bit because you know me. I'll just tell you that we assume that everybody goes outside and that we all explore the trails that everybody knows about all the great locations in Flagstaff. But it's very interesting because in my line of work, we work with all the schools in Flagstaff, hundreds if not thousands of students. And one of the first questions we asked is, who has been hiking over the weekend with their families? And you'd be surprised that less than half of the hands come up. So we know that not everybody gets to explore our amazing trails and open spaces. And so I always start with Willow Bend Environmental Education Center. It's an urban outdoor garden with a few beautiful trails. And recently we added a wildlife outdoor classroom. And it's a real gem. So even if you're big hikers or if you've never been out with kids, I really encourage you to come out and explore it. There's a lot of beautiful things to see, and like I said, just hidden corners of magic. If you're past that, I highly recommend Picture Canyon. I don't know if many of you have been out there, but even if you have, there are over 600 petroglyphs out at Picture Canyon. And it's really a magical place that sort of connects the human as well as the natural aspects and puts them together in a really unique and remarkable way for young and older students to enjoy. And so I really encourage you to go and explore, connect, again, sort of the images on rocks with what the students or what your children experience from that, and the world around us. So there's an area called the Waterbird site. And it really is. We were out there once and overhead came a blue heron. And when you look at the petroglyph, and of course we don't really know when we look at petroglyphs, and it's hard for us to know exactly what the person that left them there meant, but it was very hard to not see the connection between the heron and the beautiful waterbird. So I encourage you to go explore.
Thank you. And then tomorrow?
Yes.
Science Saturday?
Yes, and we do have every first Saturday of the month at Willow Bend, every single month, from 9:30 to 11:30, we have a free event for kids and kids at heart. And every month is a different theme. So we have everything from geology to water to we have apple celebration in November. So every month is a different theme and every month is exciting. And that is probably a great place to start.
Willow Bend has been a great partner for the Festival of Science, and we are lucky to have you.
Thank you so much.
So round of applause.
Thank you. Thanks so much, everybody. Thanks so much, Brandon. It's great to see you. It's great.
Okay, that wraps up SCI Talks for 2022. Don't forget, if you are going to do the scavenger hunt, the validation code is NIETO, N-I-E-T-O. Hope to have you guys back for next year, but even before next year, we got 2 more fun days of the festival. Hope to see you at other events. So thank you very much and have a really great night.